Last lecture, we went over buffer overflows, the theory behind it. We corrupted local variables on the stack, the return address, and we managed to redirect code execution to other functions in the program. Any questions on that? That was like a pretty fundamental big topic last lecture, so please, if you have any doubts or anything.
If you have a doubt, surely 8 other people have a doubt, so don't be shy.
So, this big thing we did yesterday was we redirected code execution somewhere else in the program. We could access functions we weren't supposed to. We could jump in the middle of functions. But the big question is, what else can we do, right? How do we take advantage of this to, get control of someone's computer or modify things outside the program we're working with? And that's what today's lecture is about. We kind of talked about it briefly, or people would bring it up. Can we, write code and put our own code into the program and then take advantage of that? So that's what we're going to go over today. So this is the program for today. You guys can actually do that. This is all we're going to get. And this little program is going to be able to get you full execution on someone's computer or reverse shell. You might not get admin, but you'll definitely get at least a user. So real quick, does anyone spot the issue with this program? Or want to explain it?
Yeah. Is it the gets call again?
Yeah, the gets call. But, what else? The printf is also important, right? So if we look at it, we have a buffer we can control with gets. We can put anything we want there. And gets is obviously a buffer overflow, so we can do whatever we want with it, and we can redirect program execution. But the printf is the really bad part, right? Because we're going to get a pointer to the actual program buffer, right? That's the important part. Because without this, this is somewhere on memory, and we don't know where in memory it is. We can brute force random memory locations, but that may never work. Because if it's randomized, or if there's literally gigabytes of memory or megabytes virtualized, you'll never get there, right? And the key thing that we're going to be messing with this function is that there's no other code, right? This is all I'm giving you. There's no win function, so you have to write your own code. So let's talk about that a little bit theoretically.
Hey, Steven.
Yeah.
I should have asked you before. Do you mind sharing your screen?
Oh, is it not? Is that all set?
Yeah.
Okay. So, any ideas on what we can do? Go on. People talked about this last lecture. Yeah.
Yeah, we can overflow it, and we send a program into it, and we set the mission address to that program, so we can execute any program we want.
Okay. Let's talk a little bit more specific. So, who remembers 230 stuff? Like, what is something we can do in assembly to, be malicious? Yeah.
Could we set something inside the pointer?
Okay, we could change the pointer, we can change data in the buffer, but we want to, how do I put this, break out of this program. That's like the end goal. So what can we do that will affect stuff outside of this program? Just like basic programming ideas. So,
You can get a shell.
yeah, we can get a shell. Do people know what a shell is in terms of concept? Right, a shell is just a terminal connection. Okay, we can get a shell. Shell's a good one. What else can we do? Yeah.
Is it possible to jump to another, or put a jump statement to another memory address?
Another memory address, right? But if we want to do a jump statement to another memory address, we can just overwrite the return address, right? Okay. So besides getting the shell is like the big one. If we can do that, that's better than anything else. But we can also say for some reason we can't pop a shell. We can read, open other files as long as the program has permissions for that. So people that work with Unix, or I don't know if they teach you this in 230, but the program does have permissions based off whoever runs it. So if it's running as administrator, we'll have administrator privileges whenever we open or do any syscall stuff. But if it's just something, so if we have a web server and we're exploiting a web server, it will run with the permissions of the user web server. So we won't be able to read the admin files or password files if we're running as a website. Okay. So because zoom things up. Because all memory is treated equally, in our current scenarios. We can write assembly instructions into the buffer. We can overload the buffer, change the return address, and because we know this pointer, if we read the pointer in our exploit script before we actually write the buffer, we can redirect the return address to the start of the buffer, right? And because memory is treated equally, whatever we put in the buffer will then be executed under the pretense that we don't have security options enabled. Everything you've done in the project 1 and in project 2 will not have security options enabled. And then I think in 2 weeks we go over how to bypass security. So, okay, we need to be able to generate assembly code, and that's what we're going to be going over today. So Pwn Tools, let me get a terminal, has this fun thing called Shellcraft, I think. So the first thing we want to do is just set our context, which more or less just tells Pwn Tools we're running AMD or Intel operating system. And when we generate shellcode, right, I could write that to ARM, I could write MIPS here, and it would generate shellcode for different operating systems, or not operating systems, architectures. So this is just specific to this. It doesn't really matter. I think if you don't put this, it has like ways to auto detect. So the function we want to use is ASM, right? ASM will take written assembly in like our language that we can understand, and it will generate the assembly code for us, right? So this is the assembly code for the move instruction, move RDI 0. Does anybody have something that they want to type in assembly that we can check out? Nothing? Okay. Well, let's look at push RBP. Let's set up a little bit of a function. Push RBP sub RSP. We'll subtract some 16 bytes, right? And this is what the assembly will look like. So at the start of every function, you have something roughly like this. And if you were to open a program in Ghidra and look at the actual bytes on the decompiler instead of looking at what the assembly is, it would look roughly like this. Okay. So we can now write assembly without, there's other ways to do this. You could write it and then use a tool like NASA and compile it. But we're going to do this because it's nice with Python. So what can we make our code do? Best thing we talked about is popping a shell, getting access, reading and writing files, we also said. But reading and writing files, depending on what you want to access, is tricky, again, based on permissions. Like, the main goal is usually to read password files if you're doing something like that. In this class, we'll have like flags that you can read. But again, like that's usually restricted, or maybe you can read. A common thing is if I'm hacking a website application, can I read the configuration files of the website, where usually passwords are stored for like the admin users or the boot setup stuff. And then, maybe we don't even want to leave the program, right? Maybe we can just inject our own code that will run a crypto miner for as long as the program's running, or a C2 listener, which is something that will listen for. It's kind of like if you think a botnet program, right? Does people know what a botnet is, right? It's you have thousands to millions of computers all running some exploit code that I can call to either DDoS a network or run crypto miners. So a C2 listener will just listen for the controller. It's called command and control. It'll listen for commands to either run malicious scripts or attack another target, and you'll usually have millions of these at once. So this is what we're going to do in class today, is exec bin sh. So this is popping a shell, and we'll go over the theory of this. And if we can run this equivalent in assembly, and we have a buffer overflow, we should be able to get a connection to someone's computer. Any questions so far? I'm going a little fast.
What would the assembly look like?
We'll go to this.
So I'm just confused as to how the print statement would cause arbitrary assembly to be executed.
All right, so the print statement doesn't do anything on its own. It just tells us where in memory the buffer is.
Right.
This is a very bad, it's an example of what we're looking for. Usually you can refer to something as a memory leak. So if a program will accidentally, print a pointer instead of the value of the pointer, we can get that information. Then we know roughly where stuff is on memory. A big thing in shellcoding is, okay, we'll have a range of 50 bytes of where something might be in memory, right? We don't know exactly where, so we'll add something called a not sled, which is just operations that do nothing at the start of our shellcode. So if we jump at the start within like the first 20 bytes, and we just hit those nothings, it'll just keep going until where our code actually starts, and it gives us a little leeway. But in this case, we have the exact value. Yeah.
If you're getting a remote connection from the shell, how do you specify like what port?
We'll talk about that later. That's not something we're going to do in class. So this gives us a way, what we're doing in class, this one, gives us a way to directly communicate with the server. So if this is attacker, and this is the server, what we are doing is we're talking to the server in this instance. This is us sending input, and it's like a, how do I say it? It's us going outwards connection. But usually in corporate networks or whatever you're dealing with, is a firewall. So in real life instances, the firewall will block incoming traffic. You don't want, unrestricted. You don't want remote access to your servers, right? So firewalls will most likely block stuff like this. So you can do something called a reverse shell, where the server will send you, it will basically ping outside and ask for information. The server will still run a shell on its local computer, but it'll send outwards traffic for all the inode, which in case usually bypasses firewall restrictions. But we won't be doing that here. We'll talk about it in theory like last slide. Anything else?
Do firewalls just like scrub input for like things they don't want to have happen?
More or less. Or like they'll if things they don't scrub, they'll just not allow at all. So usually, you block certain ports, so you only let traffic say on port 80 for one site, stuff like that. Anything else? Yep.
Why the memory address matters if we can just overflow and send some program?
Okay, so we can overflow and change return address to anything, right? So if we wanted to jump anywhere in program in the code, that's fine. But memory is allocated at the start of runtime, and we don't know where that is. Okay, so anything on stack or heap, we need some reference to where it is because we won't know beforehand.
Can we just, let's see, like move n lines to the up?
Just keep running it like 10 lines higher until it works.
Yeah.
You can, but memory is very large, and for us to run, okay, say this exploit will most likely crash the service, right? So doing that will most likely shut down whatever you're trying to attack because you keep changing return address and it'll crash after that if it's not valid. So if you want to test this locally, sure, you could do that. You could run the program, thousands to millions of times. But if I'm attacking someone else, they'll probably find out that it's crashing and block me or whatever, You'd have to be very lucky for that to work, like 1 in millions. Anything else? Okay. So this is what we want to run. Bin sh is one shell. You can do bin bash. Bin sh is just nicer because it's shorter. It means we have to do less work. So let's go over how the computer actually does stuff like execcd. So it's a syscall in Linux, right? Do people know what syscalls are? For those that don't, syscalls are operations that the computer needs to complete, but are not trusted to individual programs. So you can think read, write, execute, opening sockets, starting other processes. These are things that no individual program should do, but the operating system needs to do thousands of times a second, right? So whenever we want to call a syscall, we give up ownership of the program until the operating system's done, and then we get an interrupt signal. This is operating system theory, but we get an interrupt signal which returns execution to the program. basically all you need to know is it's like a function call. We set up the parameters and we call it, and then hopefully the kernel and the operating system does whatever we want it to. Syscall is an assembly though, right? We just said operations are userland. They can't be trusted. So programs actually have memory regions for the kernel to use, but when we are running the program and running exploit scripts, we will never have access to that because the kernel has a lot of protections against it. Gilbert, do you want to speak more on that? Or,
Kernel protections?
yeah, kernel memory protections.
I mean, from userland, you can't do anything with it either way. In kernel mode, it has like similar protections. Without like covering userland protections, it's not.
We can talk about it in 2 weeks then. Okay.
I'll introduce it more.
But the main thing is syscalls are triggered with the opcode syscall. Syscall is mostly, again, if you've done operating systems, an interrupt. If we go to 32-bit Intel, it is an interrupt, and they change the opcode in 64-bit. But let's look into that a little bit. So this is how syscall works. So again, syscall you can think as a function, right? And it uses the registers as parameters also. So RAX determines which syscall is being triggered, and then the normal registers are the parameters of this function, right? So if we want to execute a read of a file, we set RAX to 0 to indicate that it's a read syscall. RDI will be our file descriptor, and then the buffer we're reading into, and then the count of how much we want to read into. This is a link to all the syscalls. I think I have it pulled up here. Yeah. So this is a website I very much refer to all the time. That's basically every syscall in Linux. I think it's up to date. They always change stuff in here. But you can see there's a ton of syscalls, most of which no one will ever use, but they exist for operating systems and kernel stuff, right? And it just keeps going. Any questions on syscalls? So the one we just talked about, which we want to do, execCVE, is a syscall. And so let's look up execCVE in the syscall table, right? And we can see the RAX parameter is 59, and then it takes 3 parameters: file name, arguments, and environment variables, right? This is live. Okay. So what do we need to set up for this to work? All right. Someone want to say? If these are the 3 parameters, what are we going to need to do in assembly?
So like you move instructions to move those into the registers.
All right, so we can use move instructions, set the registers to what we want. So we're going to need bin sh in memory because that's the program we want to execute. We have to have that string somewhere. How can we have a string in memory?
Like make your character and have points or something.
Okay, so we can write it. If we want to write it into our buffer somewhere and then we know the reference to it, that's one way to do it. Is there another way to say, without typing it in manually, how can we use direct assembly to get it into memory? Yeah.
Is it the bracket notation where you can write things as pointers?
That's one way to do it. We have a pointer, we can write to it. But we can either use move operations and set it manually to a pointer location, or we can just push it onto the stack, right? We can just push values onto the stack directly, and that might use less opcodes or be more efficient. Okay, so let's actually start writing a little bit of an exploit script. Okay. All right, what should we do first? If we want to, let's go back. This is what we need to set up. What do we want to do first?
Zorax Rax.
Okay, we can do that. So what will this do?
That will 0 RAX, and then we can add to AL to get to the system call number.
Okay. Well, one thing we could do, you said add, we could run increment on RAX and then we'd do this 59 times if we want.
Or we can do an add.
Or we can do an add, or we can do a move, right? So let's just do a move for clarity right now.
Right, clear.
Actually, in that case, you don't need to clear it.
What?
Sorry.
Yeah, we'll talk about that later.
Okay. Sorry, that was my mistake.
As long as it gets it done, we'll
Yeah, okay.
take whatever in.
Wait, I'm a bit confused. So,
Mhm.
couldn't you just move 59 instead?
Yeah, but let's
Yeah,
make
I
it
was-
inefficient for now, because
I
that's the
was-
topic we're talking about.
Yeah, I was suggesting it so you could move into the low end, and you didn't have to put an entire keyword into the shellcode.
Mhm. Yeah, we will talk about efficient shellcode later.
Next, should we push the parameters onto the stack?
Yeah, okay, so which one do we want to do first? Probably set up RDI, right? Actually, let me look. I have it done already. Okay. Yeah, so let's push binsh onto the stack, right? So the most efficient way that I like to do it is we will XOR the register, right? Or was it RBX? RBX. And then we'll move. I'm just going to copy and paste this value because I don't remember it. That's just binsh. You can see in my comment, like little endian typed out in hex values. You can do like if I wanted plus equals P64, and I can type out binsh. It's the same thing, right? No more cheating. And then okay, so we want to push that onto the stack. Okay. Is there a problem with this? Notice this is 8 bytes.
Do you have to put the endings?
No, ending is already handled for you. Consider this is a string. So when we perform the operation, it will read as a string.
Then
I was going to say, isn't it like larger than the stack you handle?
No, that's fine.
strings are not terminated, so there's one extra.
There we go. So we need to push a 0 onto the stack too, right? Did I do this in the wrong order? We have to push the 0 first.
Can you push AH?
Yeah, you have to push the 0 first. We could push the AH here. Move RBX 0. Push RBX. Right.
Oh, wait, RBX is already 0.
True. Push RBX. And then this should work. Okay, so now we have a string on the top of the stack, right? It says binsh. If we wanted, we could run other things like cat, ls. Sh is just the most malicious one in this instance. Okay, what else do we need? Yep.
I have some questions.
Mm-hmm.
First of all, can you upload these files on Wheel in the future so we can
Yes.
work along?
Sorry. You remind me, make a campus wire post, and I will.
Okay, and other thing, can we go back to the code?
Yep.
Why are we XORing?
XOR just clears it to 0. So at this part in the program, we don't know the values in the registers.
Yeah.
They can be anything from previous execution. So you just set XOR or you move a value in there to clear it, and you know it's consistent after that.
XOR is more efficient than moving a 0 in?
Yes, and we'll talk about that why later.
Okay.
Anything else? Yeah?
I'm just a little bit confused on the first push RDX. Is that just pushing the null terminator?
Yeah, so it just makes sure that our string has an end byte. If our string was only 7 characters, we could write the 0 manually. But this is 8, so it fills up the whole register. Anyone else? Yep.
So that big long thing like that on our move RBX and then that address, is that like what is that? Is that just like encoding of the?
So if we were to type out binsh in hexadecimal bytes, it's that and then flipped because little endian
Right.
is.
Okay.
If I were to run this in GDB, you would see it. It would read as a normal string. Yeah.
Are we limited by the buffer size to what kind of program we can?
Yes, and that's why optimization is important. So we'll talk about that again later. Yep.
So it's like theoretical. Let's say I wanted like for more than 8 bytes, I would just like have to. So I'd push that, and then I would fill the like same register again, go with like the second.
Yeah, you just keep pushing as many times as needed. Okay. Anything else? This is good. Questions are important for this stuff. Yep.
Can we declare like nested buffers?
Nested buffers. Explain
So
that.
like this buffer space is gonna run out, so you make another buffer and a get statement that overflows that buffer.
Other classes will talk about things like that. Usually we can overflow one buffer, and if we don't completely kill the program, then maybe we can run code that gets more input, and we can do another buffer. But for now, we're going to deal with them. Eventually, you don't need buffers. Anything else? Okay. All right. So going back to what we want to accomplish, we set RAX. We put the binsh RDI. We need to make RDI point to the top of the stack. So what's the easy way to do that?
So the stack pointer with itself, because the top of the stack is 0?
Yep. No, top of stack is 0, but we want RDI to point to the top of the stack. So we can do what?
Move RSP to RDI.
Yes. RSP. So now RDI is pointing to the binsh string. And what's the last thing we need to do? Set RSI RDX to 0. No. We can't set this to other stuff. So if we wanted to run, cat, and we wanted to get the output of a file, we would need to provide argument variables for what file we want to output. And again, that's pushing to the stack, setting it to flag or whatever. But in our case, we're just going to set both to 0.
If we were going to use cat, we'd probably look for something like passwords.txt or something.
Or like Etsy password, Etsy shadow, which is what Linux uses to have user passwords. Yeah. But again, you can only read those if the program's running as root or admin, right? So maybe we can read a website configuration file, which will have SQL database passwords, right? That's a real world application that is pretty common. All right. So our shellcode should be complete, right? Let's just print the payload for now. Energy to be running, but oh, it's not like that. Let me just comment out GB. I might not like this simple stuff so far.
You should actually create the context too.
Ooh, that could also be wise breaking.
Don't you also have to send the payload to the process?
Well, I just wanted to show it for now.
Oh, okay.
But yeah, I didn't include context. All right, so this is our outputted shellcode. Let's also get the length of it, right? Because that will be important if our buffer is small.
Can you zoom in on
Oh, yeah, sorry. So the length of our shellcode currently is 42 bytes. I think the buffer is 128, so we have no issues. Let's see. Yeah, buffer is more than large enough, so no problem here. But if you can imagine, we only have a buffer of 32 bytes, then our shellcode won't work. Any questions on that? Is it obvious why the shellcode won't work? Yeah?
Can't we just move the RSP then? If it's like it won't fit on the stack, can't we just like increase the stack size to fit it?
That's not the issue. The issue is eventually, once we fill the buffer, we are going to overwrite the return address. So that would be saying like, okay, if this is our shellcode and our shellcode is larger than our buffer, the return address would end up having to be like halfway through here. And then when we were to jump back to the start of our shellcode, it would read the return address eventually as a command. So that would have won. Yep.
Wouldn't it, is there a potential for it possibly working if we never get an instance where we read the return address?
You can be very sneaky with it. So say we have something like move RBP, whatever. We could say like move return address RBP or RBX, and then have that like very luckily lined up with the return address. But I've never seen anyone do that. I think it's possible in theory.
But that wouldn't really have a purpose though.
Yeah, if you are going to that length, there's other things you can do. Do you have a question? Anyone else? Okay. So we have so far our assembly payload. What's next in the slides? This should all. Yeah.
Well, it's just another question. So I know we sorted out to like create it, but would that like have more, or would that like take up more of our shellcode space than if we were just not to sorry?
We will talk about that. Yep.
Just a general question. If we're communicating with a server,
Mm-hmm.
we don't know the internal like file layout.
Mm-hmm.
Then the server kind of obfuscate the location of the like, certain shells, like not put it in the common Linux location.
Are you saying if we like move like SH from?
Like not in.
That would break a lot of things. You can theoretically do that, but it's a lot of trouble for something.
That doesn't have any impact on this though, because you're, in this case, you're providing the /bin/sh shellcode string yourself, and then using that address into your own provided string.
Mm-hmm.
Like
he's saying like
you're executing the exec syscall, so the kernel needs to know where the kernel still needs to like know its syscalls. So
yeah, but he's saying that like we move bin.sh as a file.
That doesn't matter.
Like bin.sh does not exist.
Yeah, like it.
There's more issues that come up with that.
If you completely remove bin.sh as a binary, then yes, that is common. Like when you're dealing with embedded firmware, for example, there is probably no shell there. Then you need to like completely change how you approach it. But as like exploit protection on like actual servers, you cannot do something like that.
Real world systems will most likely never do that. And also like if you're moving bin.sh and you're concerned with stuff at that level, you probably should have secure code in the first place, right? Okay. Anything else? Yep.
One question about the context. You said the architecture is AMD64, right? Does it mean that, are we specifying the architecture locally or?
We're specifying architecture for Pwn tools. So this ASM function will write different opcodes depending on the architecture. So if I change this to, I think it will work with MIPS. And then I run this. I do not like that. Maybe MIPS is not.
MIPS is not x86.
x86 instructions.
I can't. I thought it would generate this.
No, like MIPS instructions are different. There is no push RBX and MIPS.
Oh, okay, that's what's invalid. But it will accept MIPS if I write valid MIPS assembly. Okay, yeah.
So is this assuming the server is AMD64?
Yes.
So how do we know what the server's on? Architecture-wise.
It's AMD64.
Mostly.
No, so one way you can do that is you can see what services will actually tell you people all these things. So this is anyway. So yeah, you can connect to the remote server, and then a lot of network services will have what's called a banner. So for example, the HTTP server may connect to you, and then there are headers that say what it's expecting or what it's running. Or you can just go to their web server, and then it says like hosted by IIS, which is Microsoft product, that kind of thing. Maybe even connect to their mail port, and then it will say, hello, I'm currently running this version. And so that's often called an exposure versus a vulnerability. It's not a flaw to tell people. Sorry, it's not a vector for someone to attack you to say what you're running, but it exposes what you're running, and then it narrows down like how many times they have to redo the code to work.
Nmap. Sorry.
No, go ahead.
Nmap is a very popular tool if you do pen testing. It basically has a bunch of automated scripts that will like ping services and try to figure out what they are. And with that, you can find out like someone's operating system. You can find out the versions of like HTML if they have file transfer protocols. It basically you can find out anything they're running as long as it's an open port and it responds. And then, yeah.
I just want to add, feel free to download Nmap. It's a great program. It's been around for a decade, and run it locally. You should know, like, if you were to run Nmap on like a UMass server or someone else's machine, like that's arguably the start of like you're trying to hack in. Like I've heard network administrators say like they get so many scans per second, it's like a joke to say that's really an attack. But it is an aggressive posture. It's like, what if I went into your house and started like turning the doorknob to see like whether it opens? Like you didn't exactly go in, but it's like, why are you touching my door handle? So just be aware of, only for local use.
You seem to be under the impression that people do not do this. And that normal people do not do this.
We had a Google Cloud instance running for UMass CTF last year, and within the week of me not the CTF ending and me not turning on the Google Cloud or turning off Google Cloud, we had I think like 3 trillion SSH brute forces.
So I'm just saying, like, maybe you'll never get caught, but I think in particular, if you were to scan like a UMass service from your UMass dorm, like someone's gonna like come down and be like, look, I own both of these. Like, what are you doing? So just run it locally on like a virtual machine that you're running.
Or if like this stuff interests you guys, I can give you links. There's websites for literally pen test training where they will host machines you can hack. So yeah, do it ethically.
One thing to note about the previous question that asked how do we know what it's running, in the case of exploit development, you usually want to have the actual binary so you can debug it and actually write your exploit and find the vulnerability. You're not just going to exploit some blind service because then you don't know anything about it, you can't exploit it. So in that case, you already know what it's compiled to, what architecture it is.
Yep. Yeah.
Before we go on, can you just address the issue again with the no terminator?
Yeah, so if we didn't push, okay, so here we XOR and then push, so we're pushing to 0. If we didn't, say if we have the stack and we're pushing like /bin/sh here, right? When we're reading this as a string for the syscall, if this isn't null terminated, it'll keep going up as a string, unless there's a 0 byte. So we just push a 0 to make sure that it's null terminated. Or else whatever garbage is here will also be interpreted in this command and it won't work. Any other questions? Cool. Okay. So let's actually write the rest of the attack, right? So let's run GDB on the application. We'll disassemble main. And we can see oh, this is a little funky. Oh, did I not compile this correctly? No, it's compiled correctly. So our gets function, the buffer is at -0x80. So to our payload, let's fill the entire buffer. So I'm just going to do A times length of payload, 80, minus length of the payload, right? So this just makes sure we write 0x80 bytes in total. And then we want to overwrite the RBP2. So let's just add 8 more bytes. And now we should be at the return address, right? Does that make sense? Everyone good? Okay. Real quick, because we want to know the pointer of our buffer, let's run the template and get p.readline, and let's process this. I'll just go do some Python code real quick to make sure we get it all formatted nice. Okay. And I'm just converting this stripping bytes and converting it to integer, right? So now we have the integer value of the pointer. Let's set this to buff pointer. Okay, and then we'll add it to payload for the return address. Okay, and theoretically, this should give us a shell if we didn't screw up something. Oh, I didn't set it. Okay. Okay, let's run GV now and figure out what's broke. This might be a good issue. I don't know. I've been having this weird GV issue. I don't know what's up with it recently. It just crashes when I lose. Regardless, I think the other script I pre-made works. Yes. Okay. This should be the same thing. Something's not working. I don't know what. But you can see we ran the program. We read the buffer pointer, right? I outputted it for us. We made the payload, which, let me open it. This is what this file is doing. So we read the pointer, make the payload. It's roughly the same shell code as before. Oh, I didn't do the syscall. That is it.
Does it matter if you're doing? No, sorry.
Ah, okay. Maybe this will work out. If not, we'll just go to the pre-made one. Oh, so it's on. Okay, I'll figure that out later. But this is roughly the same thing. We do the payload, and we fill up the buffer just like last time. Fill the base pointer, add the return address of the buff pointer, and we send it, and I run p.interactive. Maybe it's because I'm not running interactive. Any questions on this while I try to debug my script? Yeah.
What does P64 do?
Packs a 8-byte integer into 64 little endians. Anything else? Yeah, Josh.
Is it little endian because Arch is set to AMD64, or is it always little endian?
I believe Intel's always little endian.
No, Intel's always little endian. I'm asking if P64 packs to host endianness, or if it always packs to little endian.
I think if I change the content, do you know do it? Or?
I'm not sure, but you can, if you want, you can specify comma endian this and then specify endian this if you want to.
I think it goes off what Python's set up for and not the context. Actually, no, it probably does base what Python's set up for, and then if you specify context, it'll probably swap.
You can change the context. I think you can think of the big endian outness. Yeah. Okay.
Oh, okay, now it works. Yeah, I just didn't have this syscall. Okay, so with the template code, we now have a shell. So I'll go back to that. Yeah. We can see that. It's running as me because I'm the one that ran the program.
Okay.
But if I were to, what's the command that changed who runs the program?
You can do sudo sudo.
Yeah, but then no, for what the program runs on, even if I run it as a normal.
You need to set UID. You need to make the program set UID using chmod and also chownit.
That's not really going to work easily. That's why it's going to drop.
Wait, okay, if root were to compile this and set the execution privileges to root, this would be running as root. Actually, wait,
set UID.
No, I think it would still drop privileges.
You need to set UID if that's how you do that.
Don't do it in class. It's not going to be quick.
Yeah.
Okay, whatever. But theoretically, yeah.
The original process was running as root. That you'd inherit those that.
The issues in this case is that you're spawning and like executing a flow from like a GDB script is never going to work unless you're already, or like from Python script, so you would need to like have it run on a different terminal
and then just have it
afterwards.
Yeah.
So one terminal is called the root user run it, now the other terminal you execute the exploit on the already running process.
That's a lot of work though, so look it up. Theoretically. Okay. Any questions?
Yeah, wait, so just to talk about that, so if this was, so this is like the process you go through to figure out like how to do this, and then you would like actually, this program would be running and there would be some kind of like input, like standard in,
so,
and then you would pipe the assembly as bytes.
Yeah, so say that which is what you're going to do for the next project. Say this is running on a remote server, and instead of MyDump code, it's FTP file transfer protocol, and we know it's vulnerable. Instead of doing process, we do remote. It's literally a 5-character change for your program, and all these P read lines, set lines will just do it over the internet now, and this code should work almost exactly the same. That's all there is to it. And suddenly you go from a local program to, instead of vuln, you would also put like IP import. But yeah, that's it.
So the small node, you can no longer run your debugger against it if you have it as remote and use containers.
Yeah. Any questions? Comments?
Okay, I signed up for last. So if this is running on a port on a server as a certain user, and you pipe your input as that, you get the shell as that user running that.
Yes.
Okay.
So if we were to hack a website, right, I could be using this because it's an easy thing. So like say something's running Apache, which is like the big Linux one. If we were to get remote code execution on an Apache server, we would be the Apache user because the service starts as its own user. And then, getting an administrator from there is a different thing.
And so, maybe we should talk about defenses. So now that you know that that's possible, maybe you shouldn't run a whole system where all the services are running as root, because any exploit would then become root. So maybe you want to give each of those services their own username that have no other privileges, or there's different systems out there, like you may have heard of Kubernetes or Docker. Let's just stick with Docker. Like you may put your web server on a Docker container that has really nothing else on it. And so, sure, it's bad if they get into it, but they don't get like the rest of your system. Maybe the database is on a different, maybe with the same vulnerability, but maybe your database is on a different Docker container and you have isolated resources.
Can I show exploit DB?
Sure.
Most server platforms, as far as I know, have like different group permissions, and so as long as you're like not like a decent like sysadministrator, you probably don't have every person as root. Probably.
Probably. But this
Probably.
is why. Right?
Yeah. So going back to network mapping, and because we're on the topic of remote execution, say we run nmap and we find someone's running an outdated file transfer protocol or something that has a buffer overflow. There's widely public databases of exploits pre-made, so anyone have a service that they want to look up? Anything?
Why don't you just do FTP?
FTP, okay. Okay, now all of these are different exploits for different FTP things, and there's 1,000 entries, right? So let's search, type shellcode, because that's what we're doing in class. There's only one, but I'm sure they probably are called other things like remote or DOS, but okay. FileVilla TFTP, which is a very popular FTP client. And right here is the Python code. You provide IP, address, it generates the shell code for you, and you get a reverse shell. Right? So this stuff is very publicly available, which is a little scary.
Okay, and so then again, if you're running one of these services, you say, like, you inherit some machine or whatever, like you start a job and day one, they go, great, can you take over running this FTP, what was it, VIA?
Yeah.
Then maybe what you should do is go to the site and see if there's any active exploits for it, and if there is, like patch or consider taking it down or running in a different FTP server. Similarly, is it Trivy for Docker? I think it's Trivy. I think that's correct. Like there's if you load a particular Docker container, you can run something called Trivy on it. It'll tell you how many CVEs are available for hacking like the setup that you have, and then you would go in and patch your particular Docker. Maybe take something down that you're not running or find the latest patch. So there's the whole other side of this. Like, it's good to know about this stuff because one day it's much harder to defend against these attacks than to do them, right? Like that's kind of the point of this class. Like now that you see how easy this is, go ahead and get a job trying to like protect a few tens of millions of dollars from being stolen.
That's not necessarily true though. at least like when you're dealing with actual like modern machines, like modern like big exploits
Legacy
usually take
though.
an entire security researcher team several months to do. At least if you're like targeting big targets, like not actual human errors or something.
Oh yeah, I agree with that. Like yeah, let me agree with you by restating what I said. So if you want to attack a particular setup, then yeah, it's gonna a particular service on a particular machine. I think 3 to 4 months of figuring out how to do that. If you want to run a company that has to run, tens of services and hundreds of machines that each have known vulnerabilities, like try cleaning that all up. That's all I'm saying.
If this stuff interests you, you should play in our competition, CCPC and CPTC. It's like literally simulated corporate networks where you have to protect or attack. Okay. Any questions on this or shellcoding? We got a little bit more for today. Okay. So we got our shell. That's great. Okay, we found out how to exploit and break into someone's computer. We're not going to go much farther into what you can do after that, but let's improve our shellcode. So we talked about size. Size matters. If our buffer isn't big enough, then we're kind of screwed. And then also, depending on how we do input, certain bytes might not work because fgets will read or gets and fgets will just read any byte you want, right? They'll accept null bytes, they'll accept end lines. But if I use the function getLine, it will exit on 0xa is the, where's my marker? 0xa will, will exit the read call. And if that's something we need in our memory address, that's going to be a problem. So we need to kind of think about that stuff when making shellcode. So things we can do to make our shellcode smaller, right? We can change up assembly opcodes with stuff that do the same thing. So move RDI with XOR is always more efficient. Increment is, if you're off by one value, you can always use it. Usually it's inefficient though, compared to like a move. We already have this in our shellcode, but pushing popping is very good in case of moves, because moves often take 1 or 2 more bytes.
Hold on, can you go back to the XOR? Is that because the 0 is actually an 8-byte integer? Whereas
Yeah, well, I'll demo it.
Okay.
Having small shellcode is very interesting. Gilbert, yours is 22, right? Gilbert has the best one I'm aware of. Let me show. Should I show Storm or? Do you think?
Sure.
Yeah. Shellstorm is a public database of people making shellcode, right? And it's not just like x86. All of these are different architectures. And you can see they all do different things like exec CVE, setting up permissions, bind shells. And it just keeps going. And you can see the byte length if I make this a little bigger. Like some of them are like 30, some of them are 70. But like getting it low is usually like once you cut off 1 or 2 bytes in that region, that's like the difference between professional and anyone can do it. So let's find Intel. Intel x86 is what we're doing. Exact byte bin sh, 29 bytes, that's okay. I think there's 27 execute bin sh.
There's a 19.
There's a 19?
Right where you're
That's reboot though. That's just turning the computer off, which if that's your goal, sure. That's a good DOS attack. That's better than shutting down the service. Any questions on this? You are not allowed to copy and paste this for challenges. You will have to write your own, and we will be able to tell, so don't. Yeah?
So basically your buffer has to be large enough to hold in like whatever ASM.
Yeah. And like different architectures are more or less efficient. So like comparing 100 bytes of Lib's shellcode is not comparable to 100 bytes of Intel, but it varies.
I think the shortest possibly that I'm aware of for Linux is 22 bytes for a reliable execve shellcode. You can skip some bytes by not nulling out registers and kind of hope that they are already nulled out, but that kind of makes it unreliable. Then if you go onto Windows, for example, the shortest shellcode you'll find is like 140 bytes because Windows handles processes differently, so you can't just do an execve call or something like that and use actual shellcode that makes out a connection.
Okay, so let's actually experiment with shellcode. Okay, so I wrote this little program. We can give it two different assembly codes, and we can compare their lengths, right? So what were we testing? We're doing move, right? So let's compare move RDI 0 to XOR, right? Predictions? Which one do you think will be shorter? Josh?
It's going to be the XOR.
Yeah. Okay, so we can see the first shellcode. Is that big enough? The first shellcode is 7 bytes, and the second one is 3. So, okay, if we replace move with XOR, we save 4 bytes of memory, right? That's really good.
Why?
Why? Because if we are doing move, then we need to store 0 as an entire integer to move into it. If we did like move the lower half of the register, I'm sure it would be less, like 2 bytes. But XOR only needs to take a register as a parameter, or 2 registers.
Can you do under left? Can you do SC in the print statement? You can do dot hex open close, and then do the line below.
Yeah.
Do dot hex, and then say as the argument sep equals sep, it's like separate equals quotes basically, and then do the same for the other.
Okay.
You also want to know maybe why.
What?
You also want to talk about like what the reason why no bytes are bad.
Also, yeah, no bytes are bad because certain reads, like read functions, input functions, will take a null byte as like the end of your string, and there. There's like some function that literally reads a string.
Like scanf.
Yeah, scanf will. String copy. If our buffer is taking user input and then moves somewhere else, string copy will break on this. So we don't want null bytes in our code. Just try to see.
So try running again.
Yeah. Okay.
So that's a little.
Okay. What else do we want to check? No one else got. Let's check move RDI 0. Or what we were doing it was push. What's the alternative to push? If we want to push a null byte.
XOR plus move.
Yeah. Okay. XOR. Yeah. So instead of XOR move, let's look at how much like a push RDI costs, right? There's other ways to get pointers in memory, but push is the easiest one. So push is only 1 byte. That's really good. To set an entire 4 bytes of memory. Yep.
Add versus ink?
Yeah, we can check that out. Actually, ink is, let's check ink real quick. So if we want to increment RAX, increment's 3 bytes, which seems a little inefficient for increment, where it only takes a register variable. But if we want to...
Ink is not actually smaller than a byte add. I actually think a byte add is smaller than ink.
Yeah, it's actually, let's check add RAX 1, right?
No, it's, the thing I was talking about would be add AL.
Yeah. Okay, so add RAX is slightly more inefficient than ink. But let's check move RAX, 59, right? That's for exec CVE. And if we were to run increment 59 times, this would be much more efficient. But if we wanted to do, let me get to the syscall table. Where did I have this? If I wanted to do sysread or syswrite, it'd probably be more efficient to do increment. So you just gotta keep that in mind. Okay, any other questions?
Maybe just showcase like the 2 patterns of setting racks with like either XOR, move, or a push pop.
Oh, true. Push. I forgot you do push pop earlier. So
like do a move AL.
Yeah. So what we can do is we can push a value directly to the stack and then pop it into RAX versus XOR move.
You need to change the first one as well to move AL instead of reps.
All right, and that saves us 2 bytes. Yep.
So, because x86 has like variable length instructions, if you did it with a fixed an architecture with like fixed length instructions, these optimizations wouldn't necessarily make a difference, right?
In that case, if you have fixed length instructions, then move would be more efficient than incrementing multiple times. Or like you gotta think about stuff like that. Yeah. Because push pop would be 2 sets of instructions. Then.
Although you still want to avoid null bytes.
Yeah. Okay. Yeah.
So has anyone written a program to do these transformations?
Yes.
They seem pretty.
Punctuals will have stuff like that. Punctuals can auto-iterate. We won't teach you this because we want you to write your own shellcode. If you can look at the docs, you can probably find it though. Punctuals can auto-generate shellcode, and then you can give it bad characters you don't want in the shellcode, and it'll find alternative ways to do that. Any other questions? What else do we have for today? Okay, so like I was saying, for avoiding certain values, on the right we have all the values, and then on the left the functions that will cancel on this. So usually anything that has to do with like the end of the line is not wanted. So null bytes, 0x OAs, new lines, carriage returns, spaces, tabs, all of those can cancel a string or a read function. So we tend to look for alternatives in our shellcode when it does pop up. Sometimes you can get away with it though, because if everything's using gets or fgets, then you don't really have to worry. So how can we avoid this? Right, we said XOR, and we can put dummy values. So this is an interesting one that people will do sometimes. So if we have, say we want to put a, what is it? 64 minus 8 is 56-bit value in a register, and there will be 1 null byte, right? And how do we want to avoid that without doing thousands of increment calls? Because move will have it. We can do move rex, something like this, right? And then we can shift right rex, and this should avoid null bytes. Yeah, it does. So right, that will set the top byte or bottom byte, depending on what you're doing, to null, but we'll get the value we want if we set it correctly and not have any null bytes.
Wait, could you explain that?
SHR is shift right, so bit shift. And if you bit shift, it'll cancel out the higher bits or lower bits depending which direction you.
Okay.
Yeah.
So you're getting rid of the.
So like the 1-1 or the I should really have a 4 here would just be a dummy value that we put. Okay.
That's actually only going to shift by 1 bit.
8. There you go. Okay, so we talked a little bit more about advanced goals. One of these you're going to have to do in the next project. So if we wanted to read a file, say we can't get a shell because standard input, standard output redirecting isn't playing nice, or there's a firewall issue, we can use open, read, and write syscalls to open a file, read it into some arbitrary memory location, and then we can write that memory location into standard out, which should redirect back to us if we're interacting with the program. That one you will have to do on the project. And then the other one is like we were talking about the firewall issues. So say if there's a firewall, we can use the socket in connect syscalls to create a TCP socket connecting to us. We can use dupe too, which I don't really fully understand, but it makes it work. It will redirect all the standard input, standard output to the new socket, and then we can spawn a shell. And this will act as an outgoing request instead of ingoing, and avoid all firewall blocks. Let me see if I can find, I had some code pulled up for it somewhere. Reverse shell. That's BSD. Let's try that. This is ARM, but it'll be close enough. It uses the same syscalls. Right, so this one's setting up the sock adder if you've done networking programming. Sets up the port, the IP, and then we execute binsh and some syscalls. I don't really know this because it's ARM, but it's roughly the same thing. Any questions on that? Okay. I don't think we have much else for today. Yeah, that's the last slide. So, open discussion for today. Anyone have anything?
Do people understand like why you have to reverse for a firewall? Do you want to
Okay, yeah, so usually firewall will, if someone inside the network wants to make a request outside, like connect to the internet or connect to a service, we usually don't, we trust people inside the network. So more times, more or less, we don't care about outgoing traffic, but if someone's trying to connect or someone's trying to attack our systems, we always want to check anything incoming because anything on the internet is not trusted or should not be, at least. So that's why we always want to set up an outgoing connection if we're trying to hack something, ideally.
A lot of it also just has to do with, so it's a server. It's like when you're communicating with servers, they usually do not take your input from standard in. So like in this example where you can just use XIV. So you can't just use that because let's say the server uses the sockets to communicate, which for example a web server would do. Then you can communicate with the sockets, but if you try to spawn a shell, the socket file descriptor does not automatically get sent to you, so the shell gets spawned on the actual server and not on your computer. And you want the shell on your computer though. So in that case, you need to use this shellcode and manually duplicate the file descriptors. So in standard in, standard out, standard error, you copy them all over and onto your own machine versus via a reverse shell that like sends out to you. If that makes sense.
Mm-hmm. Any questions about that? We can talk more about, let's go through exploit DB or something. No one has anything. So we were talking about WordPress, right? I kept mentioning web exploits. So WordPress is like a common online web service template stuff. And they're probably the worst application I've ever seen, even though they're used so often. You can see they have 45,000 total entries. And I'm sure that's only half of what exists. But like a lot of this stuff is what we talked about in class, is like uploading PHP code that will do buffer overflow or has some memory vulnerability. A lot of it is web exploits like cross-site scripting or SQL because it's a website, but I'm sure you can find stuff that we literally did today in here somewhere. A lot of these will most definitely have reverse shells implemented in either shellcode or in JavaScript. I would very much think you guys should play around with this. There's a tool called Searchploit, which kind of scrapes this database and a little bit of other stuff. And you can literally type Searchploit and then any word, and if it finds a similar program in a name, it'll dump that for you.